our next topic, which is the first law of thermodynamics. So, the first law of thermodynamics is basically what we also call as the law of conservation of energy, because law of conservation of energy is basically what we call as, uh, it is a form of first law of thermodynamics. What first law of thermodynamics says is that whatever process is going on, whatever thermodynamic process is going on, in all those thermodynamic processes, the thermal energy, the energy which is present, would be kept constant. Now, in case of thermodynamics, in case of thermodynamics, in case of first law of thermodynamics, we have studied some thermodynamic variables. What are those thermodynamic variables? These thermodynamic variables includes number one, del Q, heat transfer, which represents the heat which is provided or released from the body. If the heat provided to the body, then it is known as positive heat. But if the heat is removed from the body, it is known as the negative heat, right? Likewise, if we talk about another thermodynamic variable, we have del U, which is internal energy, change in internal energy, not internal energy, but change in internal energy. So over here, del U or change in internal energy is also taken positive when temperature of the body increases, when the kinetic energy of the body increases, due to which the del U is taken positive. In ideal cases, we actually consider the increase in in ideal cases we actually consider the increase in internal energy equal to increase in kinetic energy, which ultimately leads to an increase in temperature. Likewise, if we talk about decrease in internal energy, if there is decrease in internal energy, that would simply mean that there is a decrease in the temperature. Likewise, we have got some other thermodynamic variables, P, which is the pressure, and del V, which is the change in volume, that is positive whenever there is an expansion. This is negative whenever there is a compression. And P delta V is basically what we call as a work done. P delta V is basically known as the work done, and here over here the P delta V is itself not P delta V is itself as a thermodynamic variable. That is what we call as thermodynamic variable. P is not a thermodynamic variable because it depends on the path taken, but P delta V is considered as a thermodynamic variable, which is known as the work done. Work done is positive if there is any expansion going on. Work done is negative when there is compression going on. We are going to study each and every phenomena in this case. So what does first law of thermodynamics says is that first law of thermodynamics says that whenever we provide heat to a closed system or an isolated system, whenever we provide heat to a system, whenever we provide heat to a system, whenever a system receives heat, whenever we provide heat to a system, then that heat energy which is provided, thermal energy which is provided to the system, causes to partly be utilized in an increase in the internal energy, and part of that heat is utilized in work doing work on or by the system, right? So whenever heat is provided to the system, the heat provided or thermal energy provided is equal to the increase in internal energy plus some of the work done by or on the system. For example, if we talk about del Q is equal to del U plus del W is the equation of first law of thermodynamics, because it says that heat is provided, out of it some amount of heat is utilized for increase in thermal energy and some amount of heat is provided for work done on or by the system. We can take the negative form of this law as well, such that whenever heat is released from the system, the heat released is equal to the decrease in thermal energy of the system, decrease in the internal energy of the system. Heat released of the system is equal to the decrease in the internal energy of the system, and the work done on or by the system. Decrease in thermal energy of the system, or release of thermal energy of the system, is equal to the decrease in internal energy of the system and the work done on or by the system. So these are the two major forms of first law of thermodynamics. Now, when it comes to uh, further derivations, we can also manipulate this equation in a manner that instead of getting a quantitative value of del q, we can simply make it as, we can send del w on the left hand side, and mathematically we can make it like del u is equals to del q plus del q minus del w. Del u is equal to del q minus del w. Now this is a manipulated version of this equation, in which shows that whenever there is an decrease or increase in the internal energy, then at that moment the change in thermal energy minus the work done is equal to the increase or decrease in the internal energy. Such that whenever thermal energy is provided, the energy which is excluded as the work done, the energy which is excluded after work done, is known as the change in internal energy. Such that whenever we provide heat to the system, then at that moment some amount of energy is utilized to do work, and rest of the energy which is left behind is known as the increase or decrease in the internal energy of the system, which is defined by this equation, right? And this is first law of thermodynamics. Likewise, if we talk about some other conditions in law of thermodynamics, it is known as law of conservation energy. Because why is it known as law of conservation energy? Because in all of these cases, what it actually shows is that the energy is being conserved. It is neither being created nor be destroyed in all of these cases. Such that over here, the heat, the energy which is being flown in the form of heat or thermal energy, is being converted into the internal energy, and that internal energy which is being increased or decreased is then utilized to do some work. In actual, the system works like that. Del q causes an increase or decrease in the internal energy. Let's say if there is an increase in the internal energy, del q causes an increase in the internal energy, and that increase in internal energy, in that sense, thermal energy, whenever there is an increase in internal energy due to providal of thermal energy is converted into internal energy. Thermal energy is converted into internal energy, and once thermal energy is converted into internal energy or kinetic energy, that increase in kinetic energy is then utilized to do work on or by the system. So this is a major concept. Apart from which, when it comes to isochoric process, let us understand some applications of the applications of the law of thermodynamics, such that the first application of law of thermodynamics is that, and first application says that first we need to understand what application really means. Application is basically what we call as application is basically in thermodynamic processes, if application can be created whenever we are going to put any of the thermodynamic variable constant in any sort of thermodynamic process, then at that moment we are going to find the applications of that thermodynamic process due to the constant thermodynamic variable in that condition. So let's suppose we are having first condition, which is only the isochoric process. Isochoric process, what we are having constant is volume, which means there is the volume is constant, due to which the change in volume or del V is equals to 0. Now, as we know that change in volume, if the change in volume is equal to 0, how we are going to achieve it? We are going to achieve it by by making a fixed piston. Piston of the system should be fixed. It should be fixed so that the volume cannot be altered no matter whether the work is done or not. The volume created should not be. Let me just draw the diagram once again. Alright. So volume of the piston should be kept constant. So for that we are going to use a the volume of the cylinder should be kept constant, due to which we use a fixed piston. Due to which we use fixed piston. Now in that sense, what we really need to do is use a fixed piston, due to which the change in volume would be 0. As change in volume would be 0, the work done on the piston, the work done on or by the piston would be equal to 0. Work done on or by the piston would be 0. As work done on or by the piston would be 0, then at that moment we can manipulate the equation of first law of thermodynamics, that del Q is equal to del U plus del W. Now, since work done is 0, we can simply say that the thermal energy provided, instead of causing an increase in the volume or decrease in the volume and cause thermal expansion and cause increase in the volume or decrease in the volume and cause any sort of expansion or compression, there is the utilization of that thermal energy to cause an increase in the internal energy of the system, due to which whenever there is an internal energy and whenever there is increase in the internal energy of the system, what it means that increase in internal energy will cause an increase in the temperature of the system, increase in the temperature of the system, as well as there would be an increase. As a result of increase in the internal energy of the system, the molecule's kinetic energy would be increased, due to which the temperature of the system would be increased, which is why we do. This is because the temperature is the average translation kinetic energy of the molecule, and the pressure exerted by the molecules as a result of increase in their kinetic energy on the walls of the container would be increased, due to which the pressure would be increased. Pressure and temperature both would be increased as a result of increase in the internal energy, which is due to increase in the kinetic energy. Alright, so in this sense, this is basically what we call as isochoric process. When it comes to the graph of isochoric process, it's drawn in such a manner that over here, so a graph of isochoric process is drawn in such a manner that volume is written on the x-axis as a dependent variable, pressure is written on the y-axis as the independent variable. Now, since the volume is kept constant, we are going to keep the line on the x-axis would be moving 0, due to which when the volume is kept constant, the pressure volume graph will basically have the graph as a straight line. The graph as a straight line. Why it would be a straight line? Because on the x-axis volume is kept constant, due to which there is only increase in the pressure at isochoric process in first law of thermodynamics, due to which at isochoric process the increase in the thermal energy leads to an increase in internal energy and increase in temperature and pressure, due to which the graph drawn is in such a manner that over here the volume increase is zero and the pressure increase is constant. On the other side, if we talk about slope of graph at isochoric condition. Slope of graph at isochoric condition is infinity, because we know the slope is equal to y2 minus y1 and x2 minus x1. So since x is constant, we can simply say that x is constant, due to which whatever value would be there in the numerator, it would be simply turned into an infinity value, because there is 0 in the denominator, due to which 0 being in the denominator 0 being in the denominator will cause any sort of value. Let's say if there is 8 into infinity, due to which the slope of this graph is infinity, right? On the other side, if we talk about, right, so this is the first application. When it comes to the graph, the name of the graph is isochore. On the other hand side, if we talk about a third condition, what is the application in daily life? We have studied the application in thermodynamic processes, but what is the application of isochoric process in daily life? We might have seen the explosion of gas cylinders. We might have seen the explosion of gas cylinders, explosion of batteries, explosion of gas explosion bombs, explosion of pressure cooker. All of these are processes in which the volume is kept constant. There is a fixed cylinder, there is a fixed container in which the volume of the liquid is kept constant, due to which the whenever there is an increase in the thermal energy of the system, increase in the thermal energy of the system or the heat provided is equal to the increase in the internal energy of the system. As a result of which, whenever there is an increase in the internal energy of the system, this increase in internal energy of the system will cause an increase in kinetic energy and thus ultimately lead to an increase in the temperature and pressure of the system. As a result of that increase in temperature and pressure of the system, the molecules of the system at a moment when will have the highest kinetic energy and will have the highest temperature and highest pressure exerted on the walls of the container will basically cause to explode the container, due to which it will cause to create an explosion in case of a fixed isochoric condition. So isochoric condition is measured. Isochoric condition has this explanation, such that whenever we have gas cylinders, why are these exploding? Is that whenever this kinetic energy is exceeded, that causes an increase in the temperature and pressure exerted by by the molecules on the walls of the container, due to which there is uh, an um, untolerable pressure by the walls of the container, due to which the molecule due to which the container ultimately bursts and there is a sudden explosion. So this is why explosion occurs. On the other side, if we talk about isobaric conditions are the one in which the pressure is kept constant. One more thing, in isochoric condition, I wanted to discuss something else as well, that this form can also have a negative version, such that if we remove internal energy from the system if we remove the internal energy from the system, let's say, if we remove internal energy from the system, then at that moment, that removal or decrease in internal energy of the system will be equal to decrease in thermal energy of the system. Decrease in internal energy of the system will be equal to decrease in thermal energy of the system. Decrease in internal energy of the system will be equal to decrease in thermal energy of the system. Decrease in internal energy of the system will be equal to the decrease in the thermal energy. Sorry, decrease in internal energy of the system will be equal to the decrease in the thermal energy or negative thermal energy, which means the thermal energy would be released. So in other words, decrease in internal energy of the system at isochloric condition will cause the release of heat energy from the system. So this is the thing. On the other side, if we talk about isobaric process, it is a process in which the pressure is kept constant. Pressure is kept constant due to which del P is equal to 0. But again, we do not consider del P in the equation, due to which whenever we are going to write the equation, it will become as del Q is equals to del U plus del W. In that equation, the equation will remain entirely same, but the difference which will only come is that the work done will be the work done will be maximum in isobaric condition. The difference over here would be that as the pressure is kept constant, as the pressure would be kept constant, the work done would be maximum, because the pressure being constant, not being increased, not being decreased, will cause the rapid increase or decrease in the volume of the gas, due to which the work done would be maximum. And in this system, the heat provided, the thermal energy provided, will cause an increase or decrease in the work done, will cause the heat provided will be causing the work done on or by the system. Now, if you talk about the equation, it's totally same. Only the difference would be there, that del Q is equals to del U plus value of W is P del V. So in this sense, P is a constant over here. P is constant. As P is constant, whenever we are going to increase the thermal energy, then the direct impact would be on the increase in volume, since P is kept constant. Due to which, when P is kept constant and thermal energy is provided, the increase in volume will occur, due to which the work done would be maximum as a result of isobaric processes in practical conditions. That is the reason most of the heat engines, all of the heat engines in our cars, are basically having an isobaric process occurring in them, because in those systems the heat energy provided causes the work done on or by the system to be maximum in the presence of internal energy, or in practical terminologies, because if we increase the thermal energy, the thermal energy needs to be converted into internal energy, which is an obvious thing. And once the internal energy is increased, the increase in internal energy causes to be converted into the work done, and that moment the work done will be maximum because of the del V being increased due to a constant pressure. Now, when we draw the graph of when we draw the graph So at that moment, we actually get a horizontal line which is parallel to the x-axis. Horizontal line which is parallel to the x-axis, which is known as horizontal line which is parallel to the x-axis, right? Due to which, what we can say that slope is again equal to 0, but it is not equal to infinity but equal to 0. So it has no slope because pressure is kept constant, due to which it is going to be a horizontal line. This graph is known as isobar. On the other side, if we talk about isothermal process, it is a process in which the temperature is kept constant. As a result of temperature being constant, the change in temperature will be equal to 0. Change in temperature is equal to 0. As a result of change in temperature being equal, as a result of change in temperature being equal to 0, there will be no increase or decrease in the kinetic energy of the system, because temperature is basically the average translation kinetic measure of average translation kinetic energy of the system, due to which change in kinetic energy would be equal to 0. Change in kinetic energy would be equal to 0. Change in kinetic energy will be equal to 0, right? And as a result of change in kinetic energy being equal to 0, then at that moment, the in ideal cases, what we are studying this condition is in ideal cases, because KMT is all based on ideal conditions. So in ideal cases, del U would be equal to 0 as a result of change in temperature being equal to 0. Due to which whenever del U would be equal to 0, then at that moment, what we are going to do, then what will actually happen to the equation is that due to no increase in the internal energy of the system or no decrease in the internal energy of the system, the heat provided to the system will be utilized in directly doing work. We have previously studied that the heat provided, thermal energy provided first, is converted into internal energy, and that increase or decrease in internal energy causes to do work on or by the system. But since the heat and since the internal energy is not having any sort of change in it, and change in internal energy is equal to 0, as a result of which the change in internal energy being 0 will cause the thermal energy to be directly converted into the work done. The thermal energy which be directly utilized into doing work on or by the system, rather than that causing the thermal energy to be converted first into the internal energy, and that internal energy doing would be utilized in doing work. We are going to utilize thermal energy directly to do work on or by the system. So thermal energy does not need to be converted into internal energy, and then internal energy would be doing work. That won't be the case. Rather, the thermal energy would be directly converted into the work done. The thermal energy would be directly utilized to do work on or by the system, right? So in that sense, we can simply write the equation as del Q is equals to del W. Since del U is 0, so equation becomes del Q is equals to del W. This is a positive version of this equation. If we talk about negative version of this equation, negative version of this equation can be made in such a manner that here minus del Q is equals to minus del W. Minus del Q is equals to minus del W. Right. Minus del Q is equals to minus del W. So in this case, what actually happens is that whenever there is a decrease in the internal energy of the system, whenever there is an increase in the internal, whenever there is a decrease in the internal energy of the system, it's once again not the internal energy, but the thermal energy. Whenever there is a decrease in thermal energy of the system, then the decrease in the thermal energy of the system, when the thermal energy is being released from the system, then at that moment the work is done, and thermal energy is released by the system. When the thermal energy is released from the system, then work is done on the system. When thermal energy is released from the system, then work is done on the system. At that moment, the work done on the system causes the compression of the cylinder, due to which the work done is negative. On the other side, if we talk about the increase in the internal energy of the system, whenever there is an increase in the internal energy of the system, then the work is done by the system. work is done by the molecules of the system, due to which the expansion occurs, isothermal expansion occurs, and that isothermal expansion causes the work done to be positive. So this is the equation of isothermal expansion, and this is the equation of isothermal compression, because the pressure exerted on the piston, the pressure exerted on the system causes a decrease in the thermal energy of the system, as a result of which the compression of the molecules occur due to decrease in the volume, due to which the work done is negative. So these are the two conditions over here. On the other hand side, if we talk about isochoric conditions, in isochoric conditions there is no expansion or compression going on. Reason behind it is that the temperature is kept, and reason behind it is that volume is kept constant, due to which work done is equal to zero, due to which there is no expansion or compression going on. But here compression is going on because work done is involved with a direct relation of thermal energy, and thermal energy is being directly converted into the work done, due to which this is how it occurs. On the other hand side, we talk about the final process. This is a adiabatic process. Before discussing that, I just like to clarify a few other points which are present in isothermal process. That in isothermal process, the thermal process, isothermal process, isothermal process needs to be done in practical terms as well. If we want to implement isothermal process in practical terms, then what we are going to do, we are going to utilize non-conducting walls. Non-conducting walls are supposed to be utilized. Non-conducting walls of the cylinder, walls of the cylinder should be non-conducting, and the alongside the non-conducting walls of the cylinder, alongside the non-conducting walls of the cylinder, the base of the cylinder is basically placed on the top of a heat reservoir or a thermal reservoir. The function of the heat reservoir, thermal reservoir, is to make sure that there is no increase or decrease in the internal energy by keeping the thermal energy absorbed or released by the system constant, due to which it causes to reserves the heat of the system, reserves the internal energy of the system, due to which the internal energy of the system is kept constant. So heat reservoir is placed, due to which the isothermal processes occur. Otherwise, it is not possible in practical terms to utilize the isothermal process. And no system is 100% isothermal, because if there's 100% isothermal, then it's going to create an increased efficiency, and that's not possible in any system till now. On the other side, if we talk about adiabatic process is the one, it is, since all of the processes which we have studied, isothermal, isobaric, isochoric, are basically what we call as the processes which were considered in closed system. Those were the processes considered in closed system. But a diabetic process is the one which is considered in isolated system. A diabetic process is the one which is considered in isolated system, right? A diabetic process is the one which is considered in isolated system. And in isolated system, what actually happens is that there is no transfer of matter, as well as there is no transfer of energy, due to which, when transfer of energy would not be there, then the change in thermal energy or the heat released or absorbed by the system would be equal to zero. As a result of heat released or absorbed by the system would be equal to zero. As a result of heat release or as of by the system equal to zero, what the system will do will cause what the system will need to do is utilize its internal energy. If the system needs to undergo an adiabatic expansion, then at that moment it needs to undergo and the use of its internal energy to go in adiabatic expansion. Likewise, if the system needs to go adiabatic compression, then the internal energy of the system would be responsible for the supply of energy for the work done on or by the system. We are going to study them individually. So if we consider the equation which we have previously written, del q is equal to del u plus del w. Now, since the change in thermal energy is equal to 0, what we consider over here is that del Q is equal to 0. So, 0 is equal to del U plus del W, right? Now, what does this equation shows us? Equation shows us that the work done on the system or by the system plus the work change in internal energy is equal to 0, which means that work done on or by the system is equal to the decrease in the decrease or increase in the internal energy of the system based on the type of um, process which is occurring. If it is, let's say, our first application, adiabatic expansion, adiabatic expansion, if let's say if this is adiabatic expansion, what actually happens in adiabatic expansion is that the work is done by the system. In adiabatic expansion, the work is done by the system because in in adiabatic expansion the work is done by the system, due to which there is an increase in the volume of the system, due to which, let me just draw a piston, due to which there is an increase in the volume of the system. There is an increase in the volume of the system, due to which the work done would be positive. And as a result of the work done positive and work done by the system, the work done by the system will cause the utilization of the internal energy of the system to do the work, because we don't have thermal energy over here, due to which the internal energy would be utilized to do the work, as a result of which the internal energy would become decreased and the work done would be positive, due to which in mathematical terms we can write this in this condition of adiabatic expansion as minus del u is equals to plus del w, minus del u is equals to plus del w, or the work positive work done is equal to the decrease in the internal energy of the system. Likewise, if we talk about compression, adiabatic compression, what actually happens in adiabatic compression is that within the adiabatic compression is that again what we are going to do is to have work done on the system rather than work done by the system. We are going to have work done on the system. So for that, work done on the system, work done on the system, due to which work done on the system will cause the work done on the system will cause the decrease in the volume of the system, because work is being done externally on the system, as a result of which work is being done externally on the system, due to which the pressure would be increased and the volume change in volume would be negative, due to which the volume would be decreased, as a result of which change of volume would be negative. As a result of which, whenever there is work done on the system, pressure would be increased, volume change in volume would be negative, as a result of which the work done overall would be negative, because the change in volume would be negative, due to which work done would be negative. And as a result of work done be negative, there would be an increase in the internal energy of the system, due to which in adiabatic compression what we actually have is that there is the negative work done minus del W is equal to increase in the internal energy of the system. Why does that occur? Because when molecules come closer to each other, at that moment there is an increase in the internal energy, as they tend to start to move, start to create repulsions among themselves, as well as they tend to move away from each other, due to which the also they try to create intermolecular forces between them, as a result of which there is an increase in the internal energy of the system. So in that sense, this is a basic concept about it. Sorry, there won't be any sort of intermolecular forces. Rather, there would be an increase in the kinetic energy of the system, because the molecules will start to repel themselves and start to move, start to uh, increase their kinetic energy to you know um, is- to move away from each other, due to which the increase in thermal energy will occur as a result of the negative work done. So this is a basic example of adiabatic compression. And one more thing, that adiabatic compression is an exponential process. We might have studied in this that the speed of sound is was rectified by utilizing by utilizing a constant gamma as an exponent over v. So at that moment, PV gamma was considered as constant. So why was gamma included over here? Gamma was included because temperature was being continuously varied. The temperature was continuously being varied whenever the sound waves were being created. But the thing which was being kept constant at that moment was the adiabatic, the transfer of heat, which means del Q was zero whenever we are producing sound waves. As a result of which, the varying temperature and adiabatic adiabatic process involves an exponential factor, which is known as the gamma, due to which whenever we draw the graph of adiabatic process whenever we draw the graph of adiabatic process, then we have p. Of course, it's going to be a PV graph. Then it is going to be an exponential graph. It's going to be an exponential graph, and that's showing a negative correlation, because pressure and volume are inversely related. Now this is what we call as an exponential graph, a graph of adiabatic expansion. And one more thing, if we talk about isothermal expansion graph, that would be a hyperbolic graph, rather than it would be an hyperbolic graph. It will be an hyperbolic graph. What does that mean? This means that this hyperbolic graph will have a smaller slope, whereas the exponential graph would be having a bigger slope. Exponential graph has a bigger slope, which is the gamma. Exponential graph of the adiabatic process is having a bigger slope, which is the gamma, and the isothermal graph will be having a smaller slope, as a result of which the adiabatic process is a quick process in which the expansion and compression occurs quickly, and in isothermal process the expansion and compression occurs quite slowly. So whenever there's an adiabatic process, the expansion and compression occurs rapidly, and there is del T not equal to 0, del Q equal to 0, and the process is done in an isolated system. So as a result of process done in an isolated system, there's a rapid change in there's a rapid change in volume with respect to pressure, and as a result of thermal reservoir which is utilized in the isothermal process, the as a result of thermal reservoir which is utilized in the isothermal process, the expansion and compression of the molecules is quite slow, as a result of which the graph is having smaller slope. So in that sense, this is basically the same condition again. The graph of isothermal and adiabatic process is same. The only difference which comes is that the only difference which comes is that the graph of isothermal process is the slope of isothermal process is smaller, and the slope of adiabatic process is bigger. And whenever we are going to represent compression is the process in which the volume is reduced, in which the change in volume is negative, due to which for compression we are going to utilize this symbol, the arrow going downwards. If you are going to utilize expansion, let's suppose expansion has the formula. For expansion, what we are going to do is, for expansion we are going to utilize this symbol rather than that symbol. So this is how we actually do it. For compression, this symbol is utilized, and for expansion, the opposite symbol in the opposite direction is utilized. So this is how we actually uh, signify adiabatic expansion compression or isothermal expansion compression. And again, there's a particular name for this graph as well. Adiabatic graph is known as adiabate, and isothermal graph is known as isotherm. So the applications of adiabatic graph and practical terminologies the is in the in practical terminology. The adiabatic process occurs in the traveling of sound waves in the form of compression and rarefaction. And second condition is the formation of cloud in the atmosphere. What actually happens whenever there is an adiabatic compression going on due to due to an increase in the internal energy of the system and the negative work done on the system, then at that moment it causes to create the causes the air molecules to condense together in the adiabatic compression, as a result of which clouds are created, and those clouds are then formed in the atmosphere in the sky. And for the third process, it is also utilized, um, adiabatic compression and expansion. Adiabatic expansion basically occurs. There's another process as well, which number one includes the speed of sound. Number two is the formation of cloud in the atmosphere. And number three is the Joule-Thomson effect. Whenever we are going to, as we might have studied in chemistry, the Joule-Thomson effect works on the basis of adiabatic expansion and compression, such that whenever there's a whenever there's a rapid um, expansion of gas molecules from a tiny nozzle, then it causes the gas molecules to cool down. Then it causes to cause a decrease in internal energy due to the work done by the system as a result of sudden expansion through a tiny nozzle. And that effect is known as Joule-Thomson effect, which works on the phenomena of adiabatic expansion. So this is also a formula to be noted. This is also a condition to be noted, and that's all about today's video. Hopefully we will do another video.